Hi, and welcome to High School Physics Explained, and I'm Paul, and today I want to go through the 2015 HSC Physics paper in the multiple choice. There are 20 multiple choice questions that relate to the New South Wales curriculum of physics, and my suggestion is that you have a pen and paper ready, that as I go through the answers, that you would pause the video as I go through each of the questions, and do the question yourself, and then listen to the explanation. I'll not only talk about the physics of the question and also why the physics of some of the responses is incorrect, but I also will spend a little time on how to read the question properly so that you approach the question correctly. So it's not so much about the physics as well, but also the technique of answering multiple choice questions. So let's get started. By the way, also that in the HSC New South Wales curriculum, the questions are organised not in terms of topics, and you'll notice here this is a motors and generators question, which is done later in the course. They are done in increasing difficulty. So questions 1, 2, 3, 4, 5 should be relatively simple questions, or at least a strong physics student shouldn't have any problem with those. And then, of course, the latter section of the questions may be more challenging and requires more analysis and deeper thinking. All right, so this question one is about the galvanometer, and here we have a question with a picture, and it says, what is the purpose of the spring in the galvanometer? Is it A, to ensure a uniform force on the coil, B, to complete the circuit through the coil, C, to counteract the motor effect of the coil, and D, to increase the magnetic flux of the coil? Pause now. Okay, so let's have a look at the question. So we have a very simplistic diagram of the diagram. You've got a north pole and a south pole here. We can see curved surfaces here, which ensures that the magnetic field lines remain parallel to the plane of the turn. And you should know that, of course, that the turning force here is determined by the torque, which is equal to BAIN. And in a motor, of course, because B is constant, A is constant, and the number of turns is constant, then the amount of turning force, okay, in this case, will be dependent solely on the current, and in fact directly proportional to it. But of course, this is that as this starts to turn, then what happens is if the current applies, it'll continue to turn. Now, the amount of force, we want it to actually stop, and it will stop when the spring force applies a force that is equal to the actual turning force. So as soon as we get to that particular point, it will start to accelerate, of course, but eventually it will come to a point where the spring force will equal out with the torque force, and therefore it will stop. And that is really the key to the question. So the purpose of the spring in the galvanometer is simply to counteract the effect of the motor effect. So the correct answer is C. Clearly A is incorrect. The magnets are responsible for ensuring the uniform force. To complete the circuit through the coil, no, that's incorrect as well. And D, to increase the magnetic flux of the coil, well, that's relating specifically to induction, and that's not related here at all. So the answer is C. Let's have a look at the next question. The diagram shows an apparatus that can be used to investigate the properties of crystals. Using this apparatus, what significant information was determined about crystals by Braggs? How well crystals reflect X-rays. B, how the atoms in the crystals are arranged. C, whether crystals exhibit the property of superconductivity. And D, whether the electrical resistance of the crystals is increased by impurities. Pause now. Well, let's have a look at the question. And this relates to the ideas to implementation section, subsection 4, which particularly relates to superconductivity. And the first part is important in understanding the fact that Bragg and Bragg had determined the crystalline structure through firing an X-ray at a crystal and got interference patterns. And that importantly, in relation to the topic, led to an understanding that metals were also arranged geometrically. Now, what was the case is that we have an X-ray over here going through collimator. So in other words, X-rays are coming off all in different directions, but this ensures we only get a single beam of X-rays. And most important here is it is the information that was determined about the crystals. So it was nothing about the reflection of X-rays. It's all actually about, in one sense, about interference. And it clearly is nothing about superconductivity. That's separate to Bragg and Bragg's discoveries. And again, whether electrical resistance of crystals is increased by impurities, that relates to semiconductors and has nothing to do with Bragg's. So really the answer is B, and how they are arranged. And as I mentioned to you before, firing X-rays therefore at metals gave similar results, and it helped us to understand that the structure of the metals and how it became a conductor. Let's look at the next question. The diagram shows a type of cathode ray tube. Which of the following statements cannot be inferred by observations made when the apparatus is shown? A. Cathode rays possess energy. B. Cathode rays possess momentum. C. Cathode rays travel in straight lines. And D. Cathode rays cannot pass through metals. Pause now. So, let's go through the question. You should be familiar with this setup. This, we know, produced cathode rays. So in other words, we had the cathode over here, and we have the anode over here. And by the way, what I'm doing here is actually representing what I would be doing if I was being a student in the HSC, is I would analyze the picture and remind myself everything I know about that. And of course, I get cathode rays coming off like this, and therefore would produce some sort of shadow over here. The most important thing is when you look at the question is a couple of those things. It cannot be inferred from observations. Okay, so what observation would you have? Well, you'd have a shadow here, and you'd know if there's a shadow here, that means the cathode rays are clearly going in a straight line. Secondly, if the fact that we get a shadow is that these cathode rays cannot pass through the metal substances here as well. The fact that they are moving and hitting and glowing over here means clearly we have some sort of energy over here. So the couple of things here is that, can cathode rays possess energy? Yeah, that can be inferred. Can cathode rays travel in straight lines? That's definitely what can be inferred. That's whole part of this particular experiment. Can cathode rays cannot pass through metals? Well, that'd be clear as again, because you'd have a shadow over here. So the answer clearly must be B. Okay, they possess momentum. Now, there was another demonstration that you would have done, but that was with the paddle wheel. And that was what the momentum was all about. So let's look at question number 4. A projectile is launched from a cliff top. The dots show the position of the projectile at equal time intervals. Assuming negligible air resistance, which diagram represents the best path of the projectile? Pause now. Okay, so let's have a look at this. All right, the most important thing understanding is this is all about projectile and projectile motion. And again, as I look through the questions, I think through projectile motion, and projectile motion says that the velocity in the horizontal direction remains constant, and the velocity in the vertical direction doesn't, is accelerated. So we would find initially larger distances and then decreasing distances and so forth. That only leads to one conclusion, and that is the fact that any projectile motion will undergo parabolic motion, okay, which is a square relationship. And so if we look at this diagram over here, if I were to draw a dotted line over here, I could clearly see that that is particularly straight here and straight here. So that discounts A. If I go over here, I have 1 and the shorter distances, and then increases, and then from here, if you look over here, this is nice and straight. That's problematic, okay, because clearly in this case the object is moving 2 blocks this way, 2 blocks this way, and then all of a sudden it's moving 1, 2, 3 blocks this way. So clearly that's not possible because it needs to be constant velocity. Here we've got 2 blocks, 2 blocks, 2 blocks. That's nice, But here we've got one block up and one block up. So we've got this straight line motion over here. So I have to discount that one as well. Let's look at D. Okay, so we've got two blocks, and so forth. So that is consistent with a horizontal velocity. And then upwards, we clearly have one block up. It's constant here, but I'm assuming that there might be a value over here. And then, of course, we have increasing distances. So therefore, it's pretty clear to me the only possible answer is D. Again, notice how I analyzed the picture and I drew in my understanding of projectile motion before I actually attempted the question. Let's go to question number 5. Why does the electrical resistance of a metal increase as temperature increases? Is it lattice vibrations increase, scattering more electrons? Is it B, electrons pair up, increasing the interactions with the crystal lattice? Is it C, fewer electrons are free to move as they fill holes in the conduction band? And D, electrons move more freely through a metal unimpeded by the crystal lattice? Pause now. Okay, so let's analyze the question. Why does the electrical resistance of a metal increase as temperature increases? Okay, we're talking about metals here. We're not talking about semiconductors. We're not talking about insulators. So therefore, as a result, we are not interested in anything to do with semiconductors. Secondly, you could also talk about superconductivity, I guess, in one sense, but we've got resistance here, and with superconductivity, there is no resistance. So as a result, when we look at the responses, electron pair up, that is all about superconductivity, and that means no resistance, so that discounts B. Fewer electrons are free to move as they fill holes in the conduction band. Well, there's a big problem here. First of all, holes don't exist in the conduction band. Holes exist in the valency band, but this is referring to semiconductors, so that therefore discounts C. Electrons move more freely through the metal unimpeded by the electrical lattices. That is totally about superconductors. They're unimpeded, so therefore we have resistance. So that discounts that response as well. A, lattice vibrations increase, scattering more electrons. That clearly talks about the connection between a cause and effect between vibrations and a slowing down because of a scattering of electrons. And lattice vibrations ultimately means an increase in temperature. So clearly A is the right response. Question number 6. Which of the following is a true statement about scientific theories such as Einstein's theory of special relativity? They are valid but unreliable ideas. B, they are useful in making predictions. C, they are concepts that lack experimental basis. D, they are ideas that can't be accepted until they have been tested. Pause now. So let's look at number 6. Which of the following is a true statement about scientific theories, such as Einstein's theory of special relativity? Is it A, they are valid but unreliable ideas. B, they are useful in making predictions. C, they are concepts that lack experimental basis. And D, they are ideas that can't be accepted until they've been tested. Pause now. Okay, now this clearly is not a question that comes out of the dot point sections that you are most likely familiar with in the HSC syllabus, but they are more related to the prescribed focus areas and understanding the nature of science. So this is a much bigger question, and it doesn't have to, although it relates to Einstein's theory of special relativity, this question actually could be addressing in any topic that relates to theories involved in science. So it's about understanding scientific theories. Okay, so you don't have to know Einstein's theory of special relativity to answer this question. And the questions have some interesting responses here. First of all, what's really important is that theories are, what is a theory? Well, a theory is a paradigm, a set of explanations with a unified idea that ties them together and is very well tested. So we talk about the theory of biological evolution, the theory of the Big Bang, and the theory of special relativity and general relativity. And when we look at all those theories, it's a unifying paradigm that is being tested multiple times. And there's lots of evidence for it. In fact, quantum theory is one of the most verified theories around. So they're clearly not reliable. Incorrect. Okay? They're clearly not unreliable. So therefore A is out. Okay? They lack experimental basis. Well, I just argued that they have lots of experimental basis, so therefore that is out as well. D is a very common thought about theories these days, that there are ideas that can't be accepted until they've been tested. You may hear this, oh, it's just a theory, it's just a belief. But the fact is, theories are very well supported. So D is out as well. That leaves us B. Well, if there's a lot of experimental evidence to support it, then they are very useful in making predictions, and that is the key answer. Question number 7. A current carrying wire is placed in them perpendicular to a magnetic field. Which graph correctly shows the relationship between the magnetic field strength, B, and the current I if the force is to remain constant? Pause now. Okay, so how would you approach this question? Well, first of all, it's about a current carrying wire placed in the perpendicular field of the magnetic field, and it's a relationship between the magnetic field strength and the current if the forces remain constant. If you know your physics, this is all about F is equal to BIL sine theta. In other words, the motor effect. Okay, so the force is determined by B, the magnetic field strength, I, the current, L, the length of wire, and sine theta being the angle that the wire is in. Well, it's perpendicular, so we can get rid of the sine theta. Secondly, the force is constant, so what we're going to do is we're going to rearrange this formula, and so you've got B is equal to F over I and L. Okay, now it's the one wire, so we now have B, and what I'm going to do is I'm not going to get rid of the L, but if I'm going to do that, then I'm going to make this A proportional to. So B is now proportional to F over I, but hold on, F is constant, so therefore B is proportional to 1 over I. In other words, the magnetic field strength is inversely proportional to the current. The only graph that represents that is C. This is a square relationship, most likely, if we assume this to be a parabola. That's not the case. This is linear, and that's not the case. This is still linear, but it's just a negative linearity, so you can't include this one either. C is the only correct answer. Question number 8. In which of the following situations does the magnetic field exert the greatest force on the proton, given that all the fields are of equal magnitude? Pause now. Okay, so going through the question, in which of the following situations does the magnetic field exert the greatest force on the proton? Well, what formula do you know that is talking about the force on a charged particle? Well, that is F is equal to QVB sine theta, where again the sine theta is the angle between the particle and the field lines. So in this case there is no velocity, so hold on, force is determined by the velocity, that automatically excludes A. B, okay, we've got a nice velocity, it's not particularly fast for a proton, but nonetheless, we have the motion being parallel to the magnetic field lines. In other words, the angle there is 0. Well, hold on, the sine of 0 is 0. So therefore, that can't be the right answer as well. Over here, we have a velocity. Clearly, we have 90 degrees between the two. And so we have a velocity v over here. And so that certainly could be a candidate. Now, the velocity here is smaller than the velocity here, but now the angle is actually 45 degrees. And if I were to just look at the velocity component, so in other words, this v part and the sine theta part, in here, that value is still 40 because the fact is that v is 40 and sine theta is, in this case, 1. But over here, it's 50 multiplied by the sine of 45. And the sine of 45 is 1 over root 2. So I've got 50 over root 2. Now this is clearly smaller than 40. And so therefore D is not the right answer. That leaves us C. Again, notice I'm drawing on my understanding of the physics formula to enable me to determine the correct answer. Question number 9. P, Q and R are straight current carrying conductors. They all carry currents of the same magnitude, I. Conductors P and Q are now fixed in place and the magnitude of the force between conductors Q and R is F. What is the net force on the conductor R when it is in the position shown? Is it F over 2 to the left, F over 2 to the right, 3F over 2 to the left, and 3F over 2 to the right? Pause now. All right, so let's understand what's going on here. Now, there are no values here, but we don't need to because we're already told that the magnitude of the force between Q and R is F newtons, okay? So in other words, there is a force over between these two distances is equal to F and R. So let's just write that down over here. There's a force over here. And in this case, this force, because these wires are therefore in opposite directions, the formula, of course, is F is proportional to I1, I2, L over D. Okay, so in this case, the D, you can see there's an inverse relationship between the force. So if we double the distance between the wires, then the force halves, okay, because the currents are all the same. So let's ask ourselves, and we're interested in on what is the force on conduction R. So therefore, F is being, okay, so if what's F, the force in this case? Well, these guys will repel. So clearly we have an F value in this direction due to Q, okay? Now, P is in the same direction, okay? But it's twice as far. So the force on R is in that direction because it's attractive. They're in the same direction. So P, but in this case, the force is half the value. I'll write it over here because of the fact that it is twice as far. So the force, we've got a full force over this way, half force this way. That only leaves, okay, as a result, a total force in that direction of F over 2. Okay? Having worked that out, makes B my only answer. And question number 9 done. Question number 10. Which of the following represents a doped semiconductor? Pause now. Okay, so let's have a look at question number 10. A doped semiconductor. Well, if it's doped semiconductor, we know our semiconductor must generally be made up of silicon or germanium. Any of those two would be fine for a crystalline structure. If it's doped, it can only be doped with either a group 3 atom or a group 5 atom. Okay, so when we look at the options there, we need silicon being the primary substance, and they're either a group 3 or a group 5 atom somewhere put in place. Okay, so let's have a look at A. We've got lots of silicon. Oh, and there's one phosphorus. Phosphorus being a group 5 atom. This seems to fit the bill, but let's make sure that that is the not the if it's correct answer. So let's look at B. Well, we have lots of carbons here, but that's a problem because carbon is not a group 3 or a group 5, so that avoids that one. Well, we've got lots of silicon here, but now we've got germanium, which is another group 4 atom, so therefore we don't count that one. And here we've got silicon here, and carbon again is not allowed. D is incorrect. So therefore A is our correct answer. I'm going to pause right now And in the second video, we'll continue on. I'll go through questions 11 through to 20. Thanks very much.